Welcome back to Applied AI Engineer. In episode 1 we made our first API call and wrote the LLM.py adapter so the provider is a one-line swap. Today we tackle the single highest leverage skill in this whole field, prompt engineering, but done in code, not in a chat window. We'll see exactly why a vague prompt and a carefully engineered one give wildly different results on the same task with the same model. Then we'll build a small, reusable prompt library from scratch, add output parsers, and learn to version prompts like the code they are. By the end, Atlas will have well-engineered, reusable prompts instead of strings buried in functions. Prompting in a chat window is improvisation. You tweak until it looks right once. Prompting in code is engineering. The same prompt runs 10,000 times against inputs you've never seen, and its output feeds the next stage of your pipeline. So it has to be reliable, it has to be parsable, and it has to behave the same way every single run. That shift in mindset from a clever one-off to a tested, versioned artifact is what this episode is about. Here's our plan for the next 15 minutes. Let's start with the most convincing demonstration in the course. We'll take one ordinary task, classifying a support ticket, and run it two ways, a lazy prompt and an engineered one. Same model, same ticket. Watch how different the two outputs are, and why only one of them is usable in software. Here's the prompt most people write first. It asks an open question, what kind of ticket is this, and drops the ticket text in. There's no role, no fixed set of categories, and crucially no instruction about the shape of the answer. It will produce something plausible, which is exactly the trap. It looks fine when you eyeball one result. Let's actually send it to the model and see what comes back. The model isn't wrong, it correctly says billing. But look at what it gave us, 3 paragraphs of markdown, bullet points, bold text, and the actual label buried at the very bottom. If your code expected a single word to switch on, this reply just broke it. And run it again, and you will get a slightly different essay each time. It's helpful prose, but it is useless as a programmatic signal. Now the engineered version. 4 changes, each deliberate. We give the model a role, so it answers in character. We hand it a closed set of categories, so it can't invent a new label. We wrap the ticket in XML tags. Claude attends to those delimiters reliably, and they keep the user's text from bleeding into our instructions. And we state the output contract in plain, forceful terms, only the category word, lowercase, nothing else. Same model, same ticket. Watch the difference. One word. Lowercase. Exactly the contract we asked for. This is the entire lesson of prompt engineering in a single comparison. The model didn't get smarter, the prompt got better. This output drops straight into a dictionary lookup or a router with zero post-processing. It costs a fraction of the tokens, and it's stable across runs. The weak prompt and the strong prompt are the same task, the engineering is the difference. Here are the two paths side by side. The weak prompt goes in and a wall of markdown comes out, unparsable, unstable, and needlessly expensive in tokens. The strong prompt goes in and a single clean token comes out, parsable, repeatable, cheap. Internalize this picture. Before you reach for a bigger, costlier model, fix the prompt. Most quality problems in applied AI are prompt problems wearing a model-shaped mask. Let's name the parts so you can build one every time. A strong prompt has 4 layers. Role, who the model is acting as. Context, the input, clearly delimited so it can't be confused with your instructions. Task 1 precise thing to do. And format the exact shape of the output you'll parse. Role, context, task, format. When an answer comes back wrong, walk these 4 and you'll almost always find the layer that's missing or fuzzy. We used XML tags and a role in passing. They're worth slowing down on because they're the 2 highest return structuring tools you have. And there's a third, even stronger one when you can't fully describe the format in words, showing examples. Let's take them in turn. XML style tags do 3 jobs at once. First, they draw a hard boundary, so a ticket that happens to contain the word ignore the above is clearly data, not a new instruction. That's your first taste of injection defense, which we'll harden in episode 14. Second, Claude is specifically trained to respect these delimiters, so they focus its attention. Third, you can ask the model to put its output inside tags too, which makes the reply trivial to parse. 1 cheap technique, 3 wins. Recall the roles from episode 1. The system prompt holds the standing rules, who the assistant is, its tone, its hard constraints. The user message holds the specific task and data for this call. A good habit, anything that's true for every call lives in system, anything that changes per call lives in user. And don't underestimate the persona. Telling the model it's a terse senior site reliability engineer versus a friendly tutor genuinely changes the structure, length, and vocabulary of every answer it gives. Sometimes the cleanest way to specify a format is to demonstrate it. This is few-shot prompting. We show the model 3 worked examples, ticket, then category, and then leave the last category blank for it to fill. The pattern is so clear that the model simply continues it. Few-shot shines for edge cases and for output shapes that are awkward to describe in prose. The cost is tokens. Every example rides along on every call, so use the fewest examples that pin the behavior. The model picks up the rhythm and completes the pattern, category, billing matching the exact format of the examples we showed it. Notice we didn't write a single sentence of instruction about formatting, the examples carried it. That's the power of few-shot. Demonstration is often a tighter specification than description. For Atlas we'll often combine both, a short role line plus 2 or 3 examples to lock behavior down hard. So far we've wanted short, clean answers. But some tasks need the model to reason before it answers, multi-step questions, anything where jumping straight to a conclusion produces a sloppy one. The technique for that is chain of thought, and the trick is to keep the reasoning out of the user's way. Here's a grounded question answering prompt with chain of thought built in. 2 variables this time, context and question. We add a grounding rule, answer only from the context, and admit it if the answer isn't there, which is how we'll fight hallucination in the RAG episodes. Then the key move, we ask the model to reason inside a thinking tag first, and only then write the final reply inside an answer tag. The reasoning improves the answer, but the user never has to read it. The model thinks through the context in the thinking block, confirms the answer is actually grounded, and then writes a tight, correct reply in the answer block. We get the accuracy benefit of step-by-step reasoning, but because it's fenced inside tags, we can show the user only the answer. This split, reason privately, answer publicly, is one of the most useful patterns you'll reuse all course long. In one picture, the prompt asks the model to reason in a thinking block first, then answer in an answer block. The thinking improves correctness, the answer is what ships. On our side, A parser pulls out just the answer tag, and that's all the user ever sees. You get better reasoning without dumping a wall of deliberation onto the person waiting for a reply. We've now written 4 prompts. Notice that each one is already a small object with a name, a version, and a template string, not a raw F string. That's no accident. Let's build the tiny template layer that makes this possible, from scratch, so nothing about it is magic. Then we'll see the LangChain equivalent. The core is a frozen data class holding a name, a version, and the template string. In post-init we run one regular expression over the template to discover every curly brace placeholder, and we cache that as the declared variables. The ID property stitches name and version into a stable identifier like Atlas classifier v2. That ID is what we'll log with every call, so we always know precisely which prompt produced which output. The render method is deliberately strict in both directions. If you forget a variable, it raises. And if you pass a variable the template never declared, a typo, a leftover name from a refactor, it also raises. Why be this harsh? Because the failure mode of a loose templating system is a silently broken prompt that ships garbage to your users. We want a typo to blow up immediately, at the call site, with the prompt's ID in the message. Fail loud, fail early. Here it is running for real. A correct render produces the prompt. Call it with no variables, and we get a clear missing variables error, tagged with the prompt ID. Misspell the variable name, and it's got just the same. The template never saw a value for ticket, so it refuses. This is the quiet reliability that separates a prompt library you trust from a pile of F strings you don't. Tiny code, big payoff. Now that you've built one, the framework version holds no mystery. LangChain ships a prompt template that does exactly what ours does. It infers variables from the curly braces and renders with format. The difference is the ecosystem. It plugs directly into chains, output parsers, and the rest of LangChain, which is why from episode 5 onward we build on it instead of our hand-rolled class. We built ours first precisely so you know what's happening underneath. Run it, and LangChain reports the same single input variable, ticket, and renders the same filled prompt our class produced. Same concept, same result, just with a much larger toolbox attached. This is the recurring pattern of the course. Build the primitive ones by hand so it's never a black box, then graduate to the framework that does it at scale. Foundations first, framework next. 2 pieces of discipline remain to turn prompts into real software, parse the reply into something you can trust, and version every prompt. Start with parsing. A prompt is only half the contract, the shape of the reply is the other half, and these parsers enforce it. Parse just tolerates the markdown fences, and surrounding chatter models love to add, then decodes from the first brace. Parsetag pulls the text out of an XML tag, pairing perfectly with our chain of thought answer block. Crucially, both raise a parse error when the reply didn't follow the format, so a malformed answer fails here instead of silently corrupting whatever comes next. Running the parsers on realistic, messy replies, just wrapped in fences and prose comes back as a clean Python dict. An answer tag yields just its inner text. Labeled lines become a dictionary. And the last line is the important one. A reply that ignored the format entirely is rejected with a clear error, not waved through. That rejection is the whole point. Bad output stops at the boundary instead of leaking downstream. In episode 3 we'll make this bulletproof with pedantic and automatic retries. Finally, versioning. We collect every prompt into a registry keyed by its ID, and callers fetch by ID rather than importing strings. Why does this matter? Because prompts drift. You improve Atlas Classify, ship version 3, and quality drops for some input you didn't test. If you logged the prompt ID with every call, you can see exactly which version ran, compare it against version 2, and roll back in one line. Prompts are code, this gives them a changelog. The registry listed out 4 named, versioned prompts, each reporting its own variables, and notice Atlas Classify is already at version 2, the engineered one that replaced our weak first draft. Resolving by ID hands back the exact template plus its description. This is Atlas's prompt layer now, not strings scattered through the codebase, but a small, auditable library you can reason about, test, and version. That's the deliverable for today. Step back and see the whole discipline. Prompts live in a registry, each with a versioned ID. A call fetches one by ID, renders it, and sends it, and logs that ID alongside the reply. When a regression appears, the ID in your logs tells you precisely what ran, and you bump the version or roll back to the previous one. Named, versioned, logged, reversible. That is what it means to treat prompts as code, and it's the habit that keeps an LLM app maintainable as it grows. One provider note before we close. Everything we engineered today, the role, the XML structure, few short examples, chain of thought, is portable. It's just text and it works across Claude, OpenAI, and open models alike. The only difference is the plumbing, where the system prompt goes in the messages list, which our LLM.py adapter from episode 1 already hides. So our prompt library sits cleanly on top of any provider. One small caveat, XML tags are reliably strong with Claude, while some other models lean toward markdown headers, so when you swap, retest your prompts on the new model. Quick recap. You saw, on one real task, how much an engineered prompt beats a vague one: role, context, task, and format. You can structure inputs with XML, teach a format with few short examples, and improve reasoning with a fenced chain of thought. You built a reusable prompt template from scratch and met its LangChain twin. And you added parsers that enforce the reply's shape and a registry that versions every prompt. Atlas now has a real prompt layer. But a parser that hopes the model returns valid JSO is fragile. Next episode, structured outputs and tool calling, we make it reliable, pydantic schemas, structured output, function calling, and automatic retries when the model returns bad JSO. See you there.